19th August 2010. In the Indian city of Hyderabad, at the most prestigious gathering in all of mathematics, the International Congress of Mathematicians, a gold medal is placed in the hands of an Israeli professor. He is the first Israeli in history to receive it. The citation reads,
"For his results on measure rigidity in ergodic theory and their applications to number theory."
To most people in that auditorium, those words sound impenetrable. What they mean is this: one man had taken a tool originally built to understand the motion of stars and used it to crack open problems that had resisted mathematicians for nearly a century. This is the story of Elon Lindenstrauss, the mathematician who bridged two universes. There is a specific kind of pressure that comes from being born into a family where mathematics is not a hobby. It is the air everyone breathes. Elon Lindenstrauss was born on August 1, 1970, in Jerusalem, Israel. His father, Yoram Lindenstrauss, was one of the most influential Israeli mathematicians of the 20th century, the man whose name is permanently attached to the Johnson-Lindenstrauss lemma, a fundamental result in the geometry of high-dimensional spaces. His mother, Naomi Lindenstrauss, is a computer scientist who earned her doctorate from Texas A&M University. Both parents were professors at the Hebrew University of Jerusalem. His sister, Ayelet Lindenstrauss, would also go on to become a mathematician. Growing up in that household meant that visiting mathematicians from around the world came to dinner. Abstract ideas were discussed across the table, not as exotic puzzles, but as everyday concerns. The family was described by those who knew them as unusually warm and intellectually generous, a home where the boundaries between work and life had dissolved completely. Elon attended the Hebrew University Secondary School, where his gift for mathematics became unmistakable. In 1988, at the age of 17, he represented Israel at the International Mathematical Olympiad held in Canberra, Australia. He returned with a bronze medal, a score of 17 out of 42, in a competition where the world's sharpest young mathematical minds gather. After high school, Lindenstrauss was selected for the Talpiot program, an elite track within the Israel Defense Forces that identifies exceptional scientific talent and places them in advanced research roles. During his IDF service, he was awarded the Israel Defense Prize. He then enrolled at the Hebrew University, earning his Bachelor of Science in Mathematics and Physics in 1991, his master's degree in mathematics in 1995, and his doctorate in 1999, all from the same institution where his parents taught. His doctoral dissertation was titled Entropy Properties of Dynamical Systems, supervised by mathematician Benjamin Weiss. The word entropy here does not refer to disorder in the physical sense most people know. In the language of dynamical systems, entropy is a precise measure of how complex the long-term behavior of a system is, how unpredictable its future evolution becomes as time progresses. The young Lindenstrauss was already asking questions at the intersection of physics-inspired mathematics and abstract number theory. By 1999, Lindenstrauss held his doctorate. He left Jerusalem for Princeton, New Jersey, to take up a postdoctoral membership at the Institute for Advanced Study, the same institution where Albert Einstein spent the final decades of his career. The next phase of his life was about to begin, and it would be defined by one of the oldest, most stubborn problems in all of mathematics. If you want to follow the journeys of the brilliant minds who connect seemingly separate universes of thought, hit subscribe right now. Join us as we uncover the human stories behind the mathematics. And speaking of connections that seemed completely impossible, let us go back to 1930. In 1930, a British mathematician named John Edensor Littlewood wrote down a deceptively simple conjecture. It concerns two irrational numbers like the square root of 2 or pi, which cannot be expressed as a simple fraction and whose decimal expansions never repeat. Littlewood asked, given any two irrational numbers, alpha and beta, is it always true that if you multiply a whole number, n pi, by the distance from n alpha to the nearest whole number, and also by the distance from n beta to the nearest whole number, that product can be made arbitrarily close to zero as n grows? In ordinary language, no matter which two irrational numbers you pick, can a single whole number always be found that simultaneously approximates both of them well enough to push a specific product toward zero? For 90 years, no one could prove it. No one could disprove it either. It sat there, a clean, accessible-sounding problem that concealed extraordinary depth. Lindenstrauss, together with mathematicians Manfred Einsiedler and Anatol Katok, attacked Littlewood's conjecture not with traditional number theory, but with ergodic theory, the study of how systems evolve over time and how their statistical properties stabilize. The key insight was to translate the conjecture into a question about the behavior of certain flows on a geometric space, and then apply measure rigidity, a set of ideas about which patterns of distribution are actually possible in such systems. Measure rigidity, at its core, asks, if a mathematical system is invariant under a rich enough collection of symmetries, does that force the system's behavior to be essentially unique, to have only one possible long-term distribution? The answer, in the right setting, is yes, and that rigidity is extraordinarily powerful. What Einsiedler, Katok, and Lindenstrauss proved in 2006, published in the Annals of Mathematics, was a landmark partial result. The set of exceptional pairs of irrational numbers for which Littlewood's conjecture might fail, must have Hausdorff dimension 0. In plain terms, exceptions can only exist within a set so thin, so sparse, that it occupies effectively no space at all on the number line. The full conjecture remains unproven to this day, but the measure of its possible failure was reduced to something almost nothing. This was not just progress on Littlewood's conjecture. It was a demonstration that ergodic theory, a field born from the study of gases and planetary orbits, could reach directly into the hardest problems of classical number theory. Lindenstrauss had built a bridge between two worlds of mathematics that had never been formally connected at this depth. But even this was not the work for which he would win the Fields Medal. There is a question in mathematical physics that sits at the intersection of the quantum world and classical chaos. When a quantum particle is confined to a surface of negative curvature, a surface that curves away from itself like a saddle in every direction, how does its probability distribution behave as its energy grows toward infinity? Does it spread out uniformly across the surface, or does it concentrate along special paths? This is the quantum unique ergodicity conjecture, formulated by mathematicians Zev Rudnick and Peter Sarnak in 1994. Sarnak, a Princeton mathematician and one of the most influential figures in analytic number theory, had spent years building toward this problem. In the arithmetic case, a specific, highly symmetric class of surfaces, Lindenstrauss proved the conjecture completely. His proof, published in a landmark 2006 paper in the Annals of Mathematics, showed that for arithmetic hyperbolic surfaces, quantum eigenfunctions do indeed equidistribute. They spread uniformly as energy grows without bound. The proof required a fusion of ergodic methods, number theory, and the theory of automorphic forms, and it was cited directly in the Fields Medal citation. Princeton mathematician Peter Sarnak, the very person who had formulated the conjecture that Lindenstrauss resolved, said of him, "He is a very deep thinker who seeks to get to the bottom of central problems by working on them for long periods, often years, and developing powerful and novel techniques as needed." In August 2010, at the International Congress of Mathematicians in Hyderabad, India, Lindenstrauss was awarded the Fields Medal, the highest recognition in mathematics, awarded every 4 years to mathematicians no older than 40. He was 40 years old. The International Mathematical Union described him as having developed extraordinarily powerful theoretical tools in ergodic theory and applying them to solve a series of striking problems in areas of mathematics that are seemingly far afield. And yet, there is something important to say here. The arithmetic quantum unique ergodicity conjecture that Lindenstrauss proved applies only to the arithmetic case. The general conjecture, for surfaces that do not carry this special arithmetic structure, remained open. Kannan Sundararajan completed a separate complementary result that, together with Lindenstrauss's work, addressed a broader form of the conjecture, but the full generalization is not settled. Lindenstrauss himself was careful not to overclaim. The incompleteness is not a failure. It marks where the frontier still stands. There is also the matter of pace. Lindenstrauss is known for working on problems for years at a stretch, accumulating depth rather than speed. This is a deliberate choice, but in the competitive culture of elite mathematics, where careers are shaped by output volume and conference presence, this approach comes at a cost to visibility and to the impatience of the field. His ascent was slower than his talent warranted, and the recognitions came in clusters. Salem Prize in 2003, EMS Prize in 2004, Fermat Prize and Erdős Prize both in 2009. The man who would crown a decade of prizes walked quietly. After the Fields Medal, the natural expectation in mathematics, as in most fields, is that the recipient enters a kind of prestigious twilight. The medal becomes a career summary rather than a midpoint. Lindenstrauss did not follow that trajectory. He held a simultaneous appointment at Princeton University, where he joined the faculty in 2004, and at the Einstein Institute of Mathematics at the Hebrew University of Jerusalem, where he was appointed professor in 2009. He has served as an editor for the Duke Mathematical Journal and the Journal d'Analyse Mathématique. He has continued to collaborate with Einsiedler, with Akshay Venkatesh, with Benjamin Weiss, on problems concerning the distribution of periodic orbits, the geometry of homogeneous spaces, and the theory of mean dimension. Mean dimension is a concept he and Weiss developed systematically, building on an idea introduced by Mikhail Gromov in 1999. It provides a way to measure the size of infinite-dimensional dynamical systems, systems so large that conventional topological dimension is not fine enough an instrument. There is a sentence from the mathematical tradition Lindenstrauss works within that captures something essential. The great ergodic theorist Harry Furstenberg, in his own laudation at the 2010 Congress, wrote that in Lindenstrauss's work, the only thing which is really needed is some form of recurrence which produces the complicated orbits which are the life and blood of ergodic theory. Recurrence. Return. The idea that a system, left to evolve long enough, will come close again to where it started. Elon Lindenstrauss grew up in a house full of mathematics, returned to Jerusalem as a professor, and now holds a permanent chair at the same institution where the discipline's architects once sat. The orbits, it turns out, were always complicated and always returning.